today I'll be talking a bit about some work I did together with Hardwick on approximate and exact selection on GPUs in different settings. The original idea or the original motivation for this work came from an algorithm which requires us to filter through a large amount of data and select an appropriate threshold such that we at the end only leave, like, for example, 10% of the data and remove all the rest. And when we're looking for implementations that we could use to figure out this threshold, we realize that there's a lot of work on sorting on GPUs, but there's not much work going on selection, which is kind of a simplified version of sorting. So first of all, let me show what the selection problem itself is. If you start off with an unsorted sequence of, let's say, real numbers or any ordered elements, then the selection problem tells you to find the kth smallest element in the ordered sequence. So you have an unordered input sequence of data, and if you order it, then you want to have the element at the kth position of your input sequence. And you find this kind of problem in many applications. You, for example, can use this to compute quantiles in statistics. You can use this to find the cutoff for top K selection, so find the K largest elements in some set. Or, as I mentioned, you can use it to select thresholds below which to filter out data. And this was our original setting. And first, let me start off with a really general framework which describes how you can implement this. Basically based around a generalized version of quicksort, which allows you to recursively simplify your problem down to a smaller problem size. So how does such a general selection framework look? I of course have a certain base case below which it usually doesn't make sense to have specific selection algorithms, below which we can just sort the data and return the value at the correct location. But if we're above this base case size, then what we do here is we pick a set of splitters from the input data. Those can be randomly picked, uniformly distributed, or something like that. In this case, if you do a randomized analysis, then usually it's best to pick them at random locations. And you can also do a certain amount of oversampling to make sure that they are well distributed over the input data. But generally, this is orthogonal to the framework itself. Then you sort the splitters, so you have them in an ordered fashion, and use this sorted set of splitters to separate the input data into different buckets. So in this case, we have 3 splitters, so we have 4 buckets. You can also imagine a minus infinity and plus infinity splitter at the end, but this is only for a conceptual understanding of the setting. And then we figure out which elements belong in which buckets. So we split our input data and group it into these different ranges. And then, based on the fact that we only want to figure out the value of a single element at a given rank, and the fact that we know that all elements from the leftmost bucket are smaller than all elements from the next bucket, and so on, we can discard all elements but those from one single bucket for which we know that they will contain the element we're looking for. And then after you selected this bucket, you do the same thing again. You select a set of splitters from the smaller input, you sort them, and you separate your data into the bucket, and so on. Recursively, you proceed like you might know from the quicksort or quick select algorithm, which this is a generalization of. You recursively proceed until you find a small enough base case such that you can solve the problem directly. And just so you see what I'm doing here on the left side, the steps I showed here are very general. What you actually do usually in the implementation is, first of all, you count how many elements you have in each bucket. because you need to decide how much space you need for each bucket. Then you compute a prefix sum over these counts to have an index range assigned to each bucket. Then you figure out which bucket contains the actual element you're looking for at a given rank. And then you copy the data out of only that bucket from the input set into temporary storage, and you you subtract the number of elements you skipped from smaller buckets from the rank, and then recursively proceed with the selection on the smaller subset of data. And this is the most general approach that I think all the algorithms that I looked at in some sense or another actually follow. So now let me show a few details on how we can actually implement this. So as I mentioned, we only need to copy the elements from the bucket we want to recursively proceed in from the input data. So we do one pass and count how many elements are in the input in each bucket. And in the second pass, we only copy out the elements from a single bucket into our output storage. And another special case which allows us to break early in this implementation is to use a so-called equality bucket in the case that we find equal splitter elements. For example, because we have many repeated elements in our input, if we have two consecutive splitters that have the same value, then the elements within this bucket will all be equal. And so if the rank that we're looking for is in such an equality bucket, then the value is actually just the lower bound of this value. And to avoid any issues in this setting, we in the end simply add a small epsilon to the rightmost splitter with the same value as all of the elements in the equality bucket to actually make it such that all the splitters are ascending. So each bucket actually has a non-empty size from 0 to epsilon here. But this is only an implementation detail which makes it easier for us to treat these equal values the same and don't need to worry about infinite recursion, which would occur in a naive implementation otherwise. So after we've dealt with this, a small look at how we select the splitters. The simplest way, as I mentioned, is to pick a small number of elements from the input data and then sort them in some way, and then pick quantiles of this input data as our actual splitters. And that's where the aforementioned oversampling comes in. So for example, if you want to have 256 splitters, then you could sample 1024 elements and pick every fourth element from the sorted output we are actually getting in the end. And now we are already moving to GPU specific stuff, because the easiest way to implement such a sorting step efficiently, since we are on a highly parallel architecture and we only have a small number of elements in my example 1024, we can implement a Betonic sort with cross-lane shuffles and shared memory accesses for the later levels of the sorting hierarchy, and basically do all of that within one single SM of the GPU, which usually makes out only the tiniest fraction of the overall runtime of our algorithm. And for actually classifying the elements, so figuring out which bucket an element belongs into after we sorted the splitters, we use a trick that was first introduced already in 2004 for the superscalar sample sort algorithm, which is we store the elements in an implicit binary search tree, which is just the order that the elements would be compared in if we were doing a binary search. So if we have a sorted set of splitters, we can of course just do a binary search to figure out which is the lower bound for the bucket our element belongs into. but that can lead to a bit complicated index calculation. So what we do instead is we use the so-called Eitzinger memory layout for binary for complete binary trees, which you might know from binary heaps. So each element has at the position 2 times its index plus 1, its first child, and 2 times its index plus 2, its second child. And that allows us to implement the traversal of a search tree in a completely branch-free fashion by just taking the result of the comparison from our current value with the from a current splitter value we are comparing with the input value from our input data set. And this can also be extended a bit more generally for architectures where you have superscalarity and so on. But on the GPU, we didn't observe much impact of trying to saturate many execution units, because basically you have so many different warps that are already present and ready to be swapped in on an SM that you didn't really need this within a single warp. So one nice thing we can also do, since in this case we limited ourselves to at most 256 buckets, we can also store the index that each element was classified into, the bucket that each element was classified into, in a single byte, and we can store this in memory to avoid having to load the element and classify it again on the second sweep where we extract the data from a single bucket. So those are the basic steps we need to do here. And just for the branch-free implementation, what we're basically doing is we compute 2 times the current index plus 1 plus the result of the comparison. So if we are smaller, we go plus 1. If we are larger, we go plus 2 compared to the splitter, and that allows us to completely traverse the search tree in a consistent code path, only having a bit of random access in the search tree itself. And that is the only issue where we somehow maybe don't do the ideal thing, because we store the search tree in shared memory and we could get some shared memory collisions, but we haven't really observed a large runtime impact of that. And now to the interesting thing, which actually made up much of my time, which I spent on this implementation. The question is, how do we count elements and how do we reduce, or how do we figure out the total counts within each bucket? There are basically 2 ways you can do this on the GPU. Both of them are based on atomics. The first approach would be to just have one array of 256 counters in global memory, and you would call an atomic add on each of these counters each time you classified an element and want to figure out or want to add it to the total count. And this, of course, means that all of the atomic operations have to collide, or will most likely collide, on the level 2 cache level, where these atomics are actually resolved on the GPU, or on modern GPUs at least. And that would allow us to run everything within a single kernel, and afterwards get out a total sum out of the atomics for number of elements within each bucket. And we tried that out, and it actually worked quite decently on older GPUs. But more modern GPUs with faster memory bandwidth and more SMs tend to have a bit of an issue with these collisions on the L2 level. So what we did as a second step instead was to accumulate the results first partially within each thread block as a shared memory atomic sum. So we have 256 counters in each thread block stored in shared memory. And afterwards, we do a reduction over these 256 elements from each thread block, which of course means we need to assign sufficient work to each thread block to have the overhead of this reduction be negligible. But in practice, that is not an issue because we have only in the hundreds SMs, but we have millions or even billions of elements we want to process maybe. And what's very important for this is that we need to have a consistent assignment from elements to thread blocks. Because if we do that, then we can also compute partial prefix sums over these shared memory atomic results, which are stored after the counting step, and use them to assign unique index ranges to each thread block and each bucket within this thread block. And this allows us to use shared memory atomics not just for counting the elements, but also later on for distributing them or for copying out the data from a single bucket without any overhead. So what this means is the left implementation for counting just uses one kernel, and the right implementation uses one counting kernel and one reduction kernel afterwards, which reduces the counts for each single bucket. And now I'll already come to the experimentation phase or the experimental results we have here, just to show you what we are doing and where we are working. I used two different GPU architectures, so the old K40 and the new V100, which span quite a lot of years and GPU architectures in between. So the performance characteristics vary a lot, and also the architectural details vary, which will matter later. And as an input, I used data sets from 2 to the 16 to 2 to the 28 elements with either all elements equal, 16 distinct elements, 128 distinct elements, 1024 distinct elements, or no equal elements, so no unique, only unique elements in the input data. And I averaged the results over the timing results over 10 runs, and did the same thing for multiple random seeds. So I think I also used 10 different random seeds and averaged the results over 10 runs of each kernel on the same input data. And for the most part, I'll show you what happens in single precision, but I also have double precision data available, which shows how well this scales for larger input data types. For correctness and comparison, I have a quick select kernel, which is based on an implementation available in the CUDA samples, but tuned or implemented with the same techniques that we used for shared memory for the SampleSelect here. And I checked the correctness using a C++ standard library implementation of quick select, which basically just makes sure that we get the same result and don't have any well-hidden implementation issues. So just so you see, I try to make everything work well, and I think except for the multiple selection, there are no I observed no issues with this implementation so far. So now let me come to the performance characteristics of this. First of all, I mentioned before the difference between global and shared memory atomics. I have here the results on the K40 and the V100 showing the throughput. So this is basically memory bandwidth with a bit of scaling for the different input sizes for the different algorithms. So here the -G algorithms are using global memory atomics. The -S algorithms are using shared memory atomics with a reduction in between. And I have quick select and sample select compared here. So what you can see on the K40, the global memory atomics win by a small or even huge margin compared to shared memory atomics. So if you have a large number of atomic counters, then the difference between global and shared memory becomes smaller. Here, the red curve is global memory, the green curve is shared memory. But if you only have a single atomic counter, which quick select needs to do, then the difference between these two values becomes huge. So this is almost almost 2.5 times higher bandwidth we can reach with quick select and global memory atomics instead of shared memory atomics. And on the V100, the image is completely reversed, which also has to do with the fact that the shared memory atomic implementation on older architectures before Maxwell was based on spinlock, if I recall it correctly. So it was basically not supported natively by the hardware and provided you bad performance characteristics for that reason. But on the V100, you see that global memory is basically completely outclassed. So the difference between 256 counters in shared memory and global memory is, I think, at least an order of magnitude. And the difference between just a single counter in global and shared memory that is much better, but still here also the shared memory atomic implementation wins. And we see that, so I didn't use a logarithmic scale here, but linear scale to have the end results more easily comparable. You see that SampleSelect largely outclasses quick select as well, basically because the reasons for that are we need less recursive invocation, so we have less recursion levels, and also we do more work on each recursion level. So quick select halves the amount of work we do in each step, while SampleSelect reduces the amount of work we do in each step by 256. And this means that after the first run, we basically only have a small remaining kernel to execute. And I also showed arrow bars here. The variation for quick select is much larger because you have a bit more randomness involved in the splitter selection, while the values for SampleSelect are pretty uniform. And if you look at the same picture for quick select, the results or the difference between SampleSelect, if you look at double precision, the difference between SampleSelect and quick select becomes even larger because, again, the amount of data we need to move is much smaller for SampleSelect because we need to read each element only once plus a small epsilon on average, while in quick select we need to read it twice on average, and also write at least once on average. And here on the V100, we basically see the same split. So the shared memory atomics for SampleSelect quickly beat quick select in both implementations. And this is now a high-level overview. I left out a lot of details here. For example, how to deal with the recursion itself, how the individual kernels are implemented and tuned. I just want to go over a few small details here. So if you look at the runtime breakdown for the individual kernels, I have here the K40 and the V100 with their respective fast atomics. On the K40, the bipartition kernel for quick select and the count kernel for SampleSelect, either with writing out the bucket index for each element as a byte or without writing it out, those are basically indistinguishable from each other. The only question is when I need to copy out the data afterwards, so filter out the elements from a single bucket. If I'm just counting the elements in a bucket, I don't have that overhead. But if I want to proceed recursively, then I have like about a third of the runtime of the counting additionally for the filtering step. On the V100 for a medium input size, we see the impact of the different kernels much more clearly. So here the bipartition kernel is maybe half of the time spent in counting the elements in each small and large set, and the other half of the time spent in copying out the elements. Whereas the V100, whereas the SampleSelect spends most of its time in counting, and for filtering out the data from a bucket, we also spend a bit of time in the reduction, which due to the medium input size brings a certain overhead, but that shrinks for larger input sizes. And one thing I also added here is The last bar in each image shows you the runtime if you copy out not the elements from one bucket, but every second bucket on the output. So that I wanted to use to show how well this works for multiple selection later on. One thing I hadn't mentioned before is how this recursion is actually implemented. And I yesterday ran a few simple examples to show the impact of our decisions and how bad they were actually in retrospect. Here I have two different implementations of the same algorithm. Using CUDA dynamic parallelism to launch the recursive subkernels, or using the host itself to launch the recursive subkernels. And this is on the A100 because I only had access to one of those at the moment. We see that the difference between SampleSelect called from the host side and SampleSelect called from dynamic parallelism device side has definite different runtime impact. So this is between 10 and 20% improvement by calling the kernels from the host. And this holds for both float and double precision, but the impact becomes smaller for other implementations. So one other thing that snuck in here, because I wanted to compare the actual runtime impact of this classification in the binary search tree, I also had another classification which just does a linear interpolation between the minimum and maximum element in the input data set. And there we see even the classification, probably due to its better representation of the input distribution, beats the linear interpolation classification, so-called bucket select from an older paper, by a certain margin. So, and one thing I also wanted to mention, a technique that is commonly used in GPU programming, especially when you deal with warp parallelism, is how you can avoid the overhead of atomic collisions. And the technique is called warp aggregation, which allows you to aggregate and partially sum up the results for an atomic operation before you apply to an atomic, by collecting all threads from the warp, which will use the same atomic counter at the same time. Basically, what we did there is we took the thread the bucket indices within the whole warp, and then we did a ballot count for each individual bit of this bucket index. So in this case, I only have 2 bits of bucket index, but in practice it would be 8. And by voting on each of these bits and combining the results afterwards into a single bit mask, we could figure out for each thread which other threads are incrementing the same atomic counter. And basically, we can use this bit mask to only increment the counter once with the sum of all incrementations we would be doing afterwards. And the impact of this, again, varies very heavily based on the architecture. Here you see the K40 and B100 again with global and shared memory atomics. For the K40, if you have a small number of elements, of distinct elements, which also means a lot of atomic collisions because they all have the same bucket index, then you can see here on the red line, the performance drops heavily. So going to the left, we have a larger number of collisions. The performance drops heavily down, and only at around 1024 elements, it becomes comparable to actually not having any collisions, or not more collisions than the average number. But if we use this warp aggregation technique, then for a smaller number of distinct elements, so more collisions, we actually got a greatly increased runtime performance. And this on the K40 holds for both shared memory atomics and global memory atomics. We see that without warp aggregation, the performance drops with a large number of collisions, But as soon as we do warp aggregation, we have a good performance or almost comparable performance to the case without any collisions above the accepted number. On the V100, the performance difference is much different because basically we see on the shared memory side almost no impact of collisions because they have native hardware support for resolving atomic collisions. We even see that using warp aggregation decreases the performance by almost 20% compared to not using them. But on the global memory side, if you're using global memory atomics, this kind of warp aggregation still makes sense. And one thing I should note with the Volta architecture, here we were doing this comparison bitwise, 1 bit at a time. But with Volta, NVIDIA also added the match intrinsic, which basically allows you to do all of these operations in a single instruction on a 32-bit type. So if you want to do warp aggregation of this type, then you can now do this with a dedicated instruction compared to manually comparing bits. And just one final plot I wanted to show on this here is the question, what is actually the impact of atomics on this setting? And again, I use the A100 as a platform because I needed to review a few benchmarks. Here, I basically want to show you the impact of warp aggregation and different atomics if I just replace all of my atomic add instructions by a normal addition in my code. Then I can see here on the shared memory side, if we don't do any warp aggregation, then the difference between shared memory atomics and shared memory accesses directly is basically negligible. So for shared memory atomics, we don't see any runtime difference or any runtime impact for using them compared to accessing shared memory directly, at least for this kind of compute memory bound kernel. But of course, if we did warp aggregation, which is kind of unnecessary in this setting, we would see that non-atomic memory accesses become more efficient because we don't because we no longer need to deal with any colliding elements in the on the hardware level. So I think this plot here on the left I just put in because it's interesting to see the comparison, but I think you shouldn't try to use warp aggregation for shared memory atomics unless you really need unless you really know that the native support performs badly. Okay, so that were the performance results for the full exact selection and different settings for the input. Are there any questions so far?
I have a question.
Yeah.
So these performance numbers look like they should saturate at some number of elements of the order of 2 to the 30 or something.
Yeah.
Can you estimate the level at which it should saturate?
Yes. So though these estimations are based on the V100 numbers because there I actually ran it to the full size ones, but my benchmark scripts just allocated too much additional memory, so I ran out of memory because I was double buffering my data. In the end, I think I was reaching with double precision about half of the memory bandwidth of the V100. But also on these saturation numbers, I didn't finely tune the work assignment and thread block sizes and number of thread blocks to different smaller input sizes. So it might be possible that you can reach this saturation way earlier. It's only here in this setting, I didn't get the, I didn't have the, since we were focusing on large input sizes, the medium sizes weren't that important to us. So basically, the peak number here you were getting was around half of the V100 bandwidth with double precision, but this involves counting also the memory writes for the bucket indices, so the bytes for each element, and the additional memory accesses for reduction and so on.
Okay, so you can actually set a limit to the number of bytes transferred per element and derive from that an upper limit, which, however, you cannot reach because you can only get to half of that.
Yes, that was roughly my estimate, but it's been a long time since I've actually done comprehensive benchmarks on this, and also learned a lot about what I've been doing wrong, but this shouldn't impact the performance too much. So I would need to benchmark this some more to figure out why we only reach half of the performance, especially since bucket selection, which doesn't use this complex search tree traversal, still has only a comparable half of the bandwidth estimate. So that would be something I would need to investigate further.
Okay, thanks.
All right. Then, if there are no further questions.
I just have a question.
Yeah.
Do you want to do this on other GPUs also in the future?
I have it implemented on AMD GPUs as well, but I didn't do comprehensive benchmarks there. We only have it available in our library where we use this kind of selection algorithm within other parts. But this I haven't tested out on any other GPUs yet, not from the performance standpoint, only that it works and is sufficiently fast.
Okay, thanks.
I have a question. Yeah. So, like we are using, like I've seen in one slide where we discussed, like we are using a binary tree inside a WOP. So, without seeing, the implementation, we can't say. But aren't there, bank conflicts happening if you are using binary tree?
Yes, definitely. So especially after, so the first level will always be a broadcast because every warp, every thread in the warp accesses the same element, but all the other elements will actually run into collisions already on the second level. You have maybe half of the elements in the first part, half of in the second part. So there is a certain amount of bank conflicts that will happen. I also tried to keep the first few levels in registers to limit the number of bank conflicts on the early levels where you would expect many of them to happen. But I didn't see a large performance impact of that. Again, I didn't do basically micro benchmarking to figure out whether this is actually the reason we don't see any difference in runtime performance. But I think also based on the fact that in the setting where all elements have the same value, I didn't see much of a performance difference, which would mean every shared memory access is a broadcast. I would guess that this doesn't have a large runtime impact. But again, you could do so many details micro benchmarks here. I just didn't have the time to do all of them.
Mm-hmm. Yeah, and one more is like in one slide you showed that the host-based, kernel invocation is better as compared to the dynamic parallelism of CUDA.
Yeah.
So so like this is like any idea like why this is happening like.
So the first of all, what I should mention is that for each recursion level that I have on the host side, I need 2 recursion levels on the device side because I need to make sure that kernels that were launched after another are actually being finished after one another. So basically what I have is I have one control kernel which only runs one thread, which then launches a sequence of kernels which need to be executed one after the other. And finally, one additional kernel, which then again in one single thread takes care of the recursion. And I think first of all, using just one thread to do a bit of control flow might be inefficient. And second of all, I think there's just so also looking from the examples for multiple selection and multi-recursion I'll show later. I think there's just a certain amount of overhead associated with the relocation that is necessary for these kernels to be executed recursively, and just a kernel launch from the device side. But I can't put any finger on where this exactly comes from. I only have the incidental numbers based on different launch patterns, which gave me good or bad performance. So I'll try to show something about this later on in the for the multi-selection.
Okay, yeah. And just the last thing, like as we discussed in the starting of the presentation, that we are running each test for 10 times and using the random numbers. So I hope that like for all the 10 times the random numbers are same. Otherwise, in the benchmarking we won't get it won't be an actual benchmarking in this case, like, because you'll get a different result every time.
Yes. So what we had basically was in actuality it's 100 tests where each group of 10 tests has the same input. So I did 10 runs to have reliable timings for the same input, and 10 different inputs to have somewhat reliable timings for different random inputs. But the important thing for all of these comparison-based algorithms is that the actual values don't matter that much. Only the order of the elements there in matters. So we could, in most cases, ignore what's. So we could, in most cases, just take elements from 1 to n and then shuffle them randomly to get a fair input for this setting.
Yeah. Thanks.
All right. So just showing you a few generalizations and modifications of this. As I already mentioned, you in some cases don't even need to do the whole recursion. You could also just get by with counting the elements. Basically, I talked about approximate selection in the title. If you stop your recursion at this level here already, when you selected your splitters and don't want to recursively proceed, or if you only count the number of elements that are in each bucket but don't group them into these buckets explicitly, then you can already get a bit of information, because you have the exact rank in the input distribution of all your splitters, and you can use that for statistical purposes, or if you only need an approximate threshold for cutting off data. And this can give you a huge performance impact, because you don't need to do all the recursion, you don't need to copy out elements, and so on. And what I wanted to show here is just what this looks like if you're looking at the precision of the rank in the total order. So how far are we off from the actual correct element, and what is the performance impact of that? And this you can see in the picture on the right. So the blue dot here is using exact selection with which doesn't give you any approximation error. And here you can see if you're using a different number of buckets for your selection and different number of splitters, what the expected approximation error in terms of the rank of your elements would be. So if you use 1024 buckets, then you're maybe you have maybe a 50% higher throughput, and you get an approximation error of around 0.1% in terms of the rank of the element you returned versus the exact element at a certain rank. And of course, it's also statistically pretty obvious. If you have a larger sample, then you have a better representation of your input. But this allows you to see how well this scales if you go down with the number of buckets and compare with different and compare the exact result versus the approximate result which you get. And here again, I averaged over 10 runs and showed the result both in terms of approximation error and input and runtime. Okay, and for the final thing, you can't just select a single element. You can also select different elements with different ranks at the same time. Basically, instead of just recursing into one bucket, you can recurse into multiple buckets at the same time. And there, CUDA dynamic parallelism comes in again. I used to two different input sizes or input data sets to basically show the best and worst case from the theoretical standpoint. The best case would be to have clustered values which group around a single rank value. So here I took 2 to the I, which are grouped around 0 as a rank. And the worst case would be to have uniform elements, because then you would need to proceed recursively in a large number of different buckets. And what I show here is the performance of a radix sort from kube, so the CUDA open source library for different sorting primitives and so on, compared with SampleSelect and QuickSelect for different input distributions. So QuickSelect with uniform distribution performs pretty badly because you need a lot of recursion in there. With cluster distribution, it performs a bit better, but still below the radix sort, which is highly tuned. And then up here for clustered values, you almost get to 2/3 of the performance for a single selection, and for uniform values you get maybe 25% worse performance. But in general, you can still use the same technique here. The only thing you need to take care of is that you don't launch too many kernels. Because what I basically did here was, instead of launching for each bucket a single kernel, if I had a large number of buckets that I need to recursively proceed in, then I launch one large kernel within where each thread block takes care of extracting and working on a different bucket. And this allows me to basically group together multiple recursive calls into a single call. And if I didn't do that, then the performance would be horrible. So I think it was even 2 orders of magnitude worse than what I get right now. Because if you launch thousands of kernels on the GPU from the device side, that just isn't efficient, because it needs to synchronize with the scheduler somehow. And just so you know how well this scales, I took the uniform example and increased the number of ranks, and show here at around 2 to the 7 elements, the radix sort implementation starts to become more efficient than my sample sort implementation, SampleSelect implementation. But you could probably improve this performance here by more finely tuning the load balancing and the work distribution to your input settings. But I didn't want to go too far here. So that basically allows you to pick out a few elements at given ranks with runtime, which can be twice as good as highly tuned radix sort. So if I want to sum this all up, the SampleSelect kernel, because it does less recursion, it does less data movement, is much more efficient than QuickSelect on both old and new architectures. We can reach around 50% of the experimental peak memory bandwidth if we're working on double precision data. Approximate selection can still be 2 times faster than exact selection, and multiple selection can beat highly tuned sorting algorithms for a large number of ranks we want to extract. And I just wanted to add a few takeaways I had here from a performance engineering standpoint, which are really overgeneralized, but I think it might be helpful to at least have seen a few examples where this is true. So here, warp aggregation usually doesn't make sense if you have some kind of hardware support for resolving atomic collisions. And the shared memory atomics in general are really fast. So if you have a memory-bound algorithm, it usually doesn't make sense to try and warp aggregate, or it usually doesn't give you a large downside from a performance standpoint if you're just counting elements. The CUDA dynamic parallelism is really nice for recursive trees, but if you have something like tail recursion, then it makes sense to implement everything on the host side because of the overhead I measured. But of course, take it with a bit of salt, because I didn't micro benchmark this too much. And finally, the the multiple selection shows that you can prune the recursion tree and sometimes get twice or even more of the performance that you would get if you ran the kernel to its base case for every part of the recursion tree. So basically, if you can cut off early and only need part of the results, then an approach like I described with the multiple selection can really help you. All right, now I talked quite a lot and I guess longer than I planned, but I hope you could take away something from this talk. I also have the 2 papers which are basically describing the 2 steps in developing this, and I'm open for any questions.
Thank you very much, Tobias, for this interesting talk. Any questions from the audience? So I have a question. When you showed the comparison between the K40 and the V100, the performance factor when going from one to the other was about a factor of 9, if I remember correctly, for the highest values you got for the largest problems. So 5 billion versus 45 billion on the NVIDIA.
Yes.
The memory bandwidth ratio between the two is a factor of 4.5, however. So there's a gap. So that's interesting because from the performance behavior in the V100, you would assume that for larger problems, you even get more performance, which would widen the gap even further. So could you say something about that?
So my guess from the experiments I ran on larger numbers, at least for parts of the kernels, but I forgot to include them here and also wanted to keep things comparable. My guess would be that the K40 is far from its theoretically achievable memory bandwidth because the atomic implementation still suffers a bit from the large number of collisions which need to be resolved on the L2 level. So on the V100, we really got within an eyeshot of the peak performance, peak memory bandwidth, but on the K40 we were far from that. So my guess would be that this has to do with the atomic performance. But again, I did do some differential benchmarks between different implementations, some using atomic, some not, and I couldn't really get to a conclusive results there. So it might also be that just the compiler doesn't emit perfect code, or the different unrolling configurations I tried actually didn't properly interleave different loop iterations and so on. So there's a lot of moving parts in here that I can mainly speculate about, but you could do a lot of experiments to figure out the details. But my guess would be it's just far from the peak memory bandwidth for K40.
All right, thanks. Any more questions? All right, then thank you again for your talk, and bye-bye, everyone.
And thanks for the invitation.